This is a video about the binomial distribution. The binomial distribution is a probability distribution which is used when an action is repeated and we're interested in the number of successes. It gives the probability for each possible number of successes, and there's a formula for calculating these probabilities. The purpose of this video is to explain the formula and show you how to use it. For example, suppose that we play a board game several times in a row. We might be interested in the probability that I win 2 out of these games. The binomial distribution enables us to calculate the probability that I will win 2 or any other number out of a sequence of games. There's a couple of things to bear in mind whenever you want to use the binomial distribution. The most important is that the probability of success must be the same in each trial. In my example, the probability of winning each game must be the same. So in particular, the trials must be independent. The outcome of one game can't affect the probability that I win the next game. Now, the most important question in a study of the binomial distribution is, what's the probability of getting x successes in a sequence of n trials? Let's look at some examples. Suppose that we play Carcassonne 3 times in a row. Let's work out the probability of winning 2 games out of 3. We can do it by drawing a tree diagram. Suppose that the probability of me winning is 1/3 and the probability of you winning is 2/3. I'll write S for me winning, S for success, and F for me not winning, F for failure. We can assume that the probability of me winning each game is the same, and that the outcome of one game doesn't affect the probability of me winning the next one. Well, you can see that there are 3 ways in which I can win 2 games out of 3. I can win the first 2 and lose the last one, or I can lose the middle one, or I can lose the first one. You can also see that each way has the same probability, because each time we'd have to multiply 1/3, 1/3, and 2/3, just in a different order. So the probability of me winning 2 games out of 3 is 3 times 1/3 squared times 2/3. And if you work that out, it's equal to 2/9. Now let's look at a different example. Let's suppose that we play 5 games of Ticket to Ride in a row. Let's work out the probability of winning 2 games out of 5. This time we'll assume that the probability of me winning a game is 1/4. Well, you can infer from the previous example that the probability of winning 2 games out of 5 will be the number of different ways in which I can win 2 games out of 5, times the probability that the first 2 games result in a win and the final 3 games result in a loss. The probability of winning the first 2 games and losing the last 3 is 1/4 squared times 3/4 cubed. Remember that the probability of winning a game is 1/4, and so the probability of losing a game is 3/4. The difficult thing is working out the number of ways in which I can win 2 games out of 5. One possibility is obviously that I can win the first 2 games and lose the remaining 3. We can find out the others by reordering the letters SS, FF, F, but we need to do it in a logical way so that we don't miss out any possibilities. To begin with, I'll keep the first S in the same place and move the second S along. That gives 4 possibilities. Now I'll move the first S along and put the second s next to it, and move the second s along. Now we've had 7 possibilities. Moving the first s along again gives a total of 9 possibilities, and moving both s's to the end gives a total of 10 possibilities. So the number of ways of winning 2 games out of 5 is 10. And that means that the probability of winning 2 games out of 5 is 10 times a quarter squared times 3/4 cubed. And if you work that out, it turns out to be 135 over 512. Now let's address the general question: what's the probability of getting x successes in n trials? Remember, this is the key question in any study of the binomial distribution. Suppose that the probability of success is p. In that case, the probability of failure is 1 minus p. So the probability of x successes in a row followed by n minus x failures in a row is going to be p to the power of x times 1 minus p to the power of n minus x. Okay, now there's some notation for talking about the number of ways of getting x successes in a sequence of n trials. You can write an n above an x and put them in brackets, or you can write a c with an n above and to the left and an x below and to the right. And both things you can read out n choose x. But remember, this is just notation for talking about the number of ways of getting x successes in n trials. So using that notation, we can say that the probability of x successes out of n is n choose x times p to the power of x times 1 minus p to the power of n minus x. So this is the key formula that you need to remember for the binomial distribution. It can be rewritten like this. In order to use the formula, though, we need a better way of working out how many ways there are of getting x successes in n trials. It's not very helpful if we have to count them all every time. First of all, because in some cases there's a very large number, and secondly, because it's easy to make a mistake when counting. Fortunately, there's a formula which says that n choose x is equal to n factorial over x factorial times n minus x factorial. For example, it means that 5 choose 2, the number of ways of getting 2 successes out of 5, is 5 factorial over 2 factorial times 3 factorial. I'll show you how to calculate this. 5 factorial means 5 times 4 times 3 times 2 times 1. 2 factorial means 2 times 1. And 3 factorial means 3 times 2 times 1. So 5 factorial over 2 factorial times 3 factorial is 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 3 times 2 times 1. This looks horrible until you realise that most of these numbers cancel out, leaving us with just 5 times 4 over 2 times 1, which you can easily see is 10. So now we can give a more helpful version of the binomial formula. We can say that the probability of x successes out of n is n factorial over x factorial times n minus x factorial times p to the power of x times 1 minus p to the power of n minus x. And this is the key formula that you need to remember in the context of the binomial distribution. There's another method for finding the number of ways to get x successes out of a sequence of n trials. It uses Pascal's triangle. Suppose we write the binomial coefficients in the form of a triangle like this, and we calculate all these coefficients. The resulting triangle is full of patterns. For example, along this diagonal are the numbers 1, 2, 3, 4, 5, and so on. Along this diagonal are the triangle numbers 1, 3, 6, 10, and so on. But the most important pattern is that each number in the triangle is the sum of the two numbers above it. For example, 3 is 2 plus 1. 6 is 3 plus 3. And 10 is 4 plus 6. We can use this pattern to create more and more rows of the triangle. For example, you can probably work out that the next row must be 1, 6, 15, 20, 15, 6, 1. Okay, well, it's easy to remember the first few rows of this triangle, and you can always construct more if you need to. Let's see how we can use it to find 6 choose 4. First of all, we need to find the row which starts 1, 6. The 1 at the end of the row will be 6 choose 0. So the 6 is 6 choose 1. The 15 is 6 choose 2. The 20 is 6 choose 3. And the 15 is 6 choose 4. So 6 choose 4 is 15. For small numbers, it's probably quicker to use Pascal's triangle than it is to use the factorial formula. But in any situation, it's up to you which method you want to use to calculate the answer. Okay, so let's summarize what we know about the binomial distribution. At the same time, I need to show you a bit of new notation. We've got a sequence of trials, and let's call the number of trials n. In each trial there's a probability of success, which we call p, and we're interested in the number of trials which result in success, and let's call this random variable x. The new bit of notation is that we can say that x follows the binomial distribution with parameters n and p. So that means that x is a random variable which has the binomial distribution where there are n trials and p is the probability of success. What we've discovered is a formula for the probabilities. We can say that the probability that x trials out of n result in success is n choose x times p to the power of x times 1 minus p to the power of n minus x. And we can also write that like this. We know that n choose x is equal to n factorial over x factorial times n minus x factorial. So we can also say that the probability of getting x successes out of n trials is n factorial over x factorial times n minus x factorial times p to the power of x times 1 minus p to the power of n minus x. Let's look at some examples. First of all, suppose we have a random variable which is equal to the number of successes in a sequence of 6 trials where the probability of success is 2/5. What's the probability of 4 successes out of 6? Well, the probability of 4 successes will be 6 choose 4 times 2/5 to the power of 4 times 3/5 squared. We know from our earlier work that 6 choose 4 is equal to 15. So the probability that x is equal to 4 is 15 times 2/5 to the power of 4 times 3/5 squared. And if you work that out, that's equal to 0.138 to 3 significant figures. Here's another example. Suppose that x has the binomial distribution where there are 10 trials and the probability of success in any one trial is 3/4. What's the probability that x is equal to 8? Well, the probability of 8 successes out of 10 will be 10 choose 8 times 3/4 to the power of 8 times 1/4 squared. We'll have to work out 10 choose 8, and let's use the factorial formula. 10 choose 8 is 10 factorial over 8 factorial times 2 factorial. That's the same as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 2 times 1. Fortunately, most of those numbers cancel out, so that all we're left with is 10 times 9 over 2 times 1, which is 45. So that means that the probability that x is 8 is equal to 45 times 3/4 to the power of 8 times 1/4 squared. And if we work that out, it's equal to 0.282 to 3 significant figures. One last example. Suppose I throw 5 dice. What's the probability of getting 2 multiples of 3? The thing we're interested in here is the number of multiples of 3. So let's say that the random variable x is the number of multiples of 3. We can say that x has the binomial distribution, where 5 is the number of trials and 1/3 is the probability of success. The chance of getting a multiple of 3 must be 1/3 because there are 2 multiples of 3 and 6 possible numbers. The questionnaire is asking us for the probability that x is equal to 2. It's asking us how likely we are to get 2 multiples of 3. And we know that the probability that x is 2 is 5 choose 2 times 1/3 squared times 2/3 cubed. Using Pascal's triangle, we can see that 5 choose 2 is 10. So the probability that we're looking for is 10 times 1/3 squared times 2/3 cubed. And if you work that out, it's equal to 0.329 to 3 significant figures.